So we finally made it to that part of the course that's actually the title of the course, right? This was a Taylor series course, and this section is on Taylor series. And perhaps you've seen this coming, because what we've been doing for the last few weeks is building up better and better approximations of a function. So we started with constant, then linear, then quadratic, cubic, fourth, right? Nth degree polynomial approximations of a function. And so what we're doing now is we're just going to say, let n go to infinity. Essentially have infinitely long polynomials. So before, it looked like this. We had f of x was approximately equal to the nth Taylor polynomial, right? And this was the nth Taylor polynomial centered at b. You had to find all those derivatives, evaluate them at b, and then multiply those by x minus b to the appropriate power divided by the appropriate number factorial, right? So now we're just saying what we want to do is we want to define the Taylor series as the limit of those Taylor polynomials as n goes to infinity. This is a limit process, so there's the notion of, does the limit converge, does the limit not converge? So we quite often say that a function, we wouldn't say necessarily that the function is equal to the Taylor polynomial, but we would say that the Taylor polynomial converges to the function, right? So it's not always true that Taylor polynomials will converge to the function that you started with, but it is quite often true, and so we will be looking at what we can do when it is, and how we can predict when it's going to work and when it's not going to work. Okay, so notice in the notation, the summation notation, which I guess I've used already within this course, but I think the book introduces it at this point right now. The sum, I mean, you've seen this in Calc 2, the sum k equals 1 to n, or 0 to n. And then you're using the index to describe things. So the kth derivative evaluated at b divided by k factorial times x minus b to the k. So when I write this summation n equals 0 to infinity, notice I switched from k's to n's. Here the n of the Tn was playing the role of the highest index, the highest power of n that I wanted. And here I'm just using n as my index, just because I like n better than k here. So k equals 0 to infinity of the nth derivative of f evaluated b divided by n factorial times x minus b to the n, and add that up for all values of n between 0 and infinity, right? And it is a limit process, right? To say take it all the way to infinity means take the limit as that upper part of the sum goes to infinity. But the start of the sum is also kind of weird, because what is the 0th derivative of b, right? When it starts with n equals 0 here, so I'm saying take the 0th derivative. Well, it's essentially saying take the derivative 0 times. So just leave f alone. So the 0th derivative of b is just f of b, right? There's also the matter of what the heck is 0 factorial, right? 0 factorial is defined to be 1. It may seem odd that it's defined to be 1, but it's every time we ever run into a pattern, like in this pattern, you're dividing by 2 factorial, 3 factorial, 4 factorial, go the other way, 3 factorial, 2 factorial, 1 factorial, 0 factorial, right, would be in the denominator. And the denominator is 1. It always turns out that we want 0 factorial to be 1, so we just define it that way. It's 1. And then likewise, x minus b to the 0 power is also 1. Now this is obviously true for x not equal to b, right? Any number to the 0 power is equal to 1, except 0 to the 0. And in a limit process, 0 to 0 is one of these indeterminate forms, and it depends on how the limit is working as to how it ends up. But in this case, it makes most sense for us just to assume that x minus b to the 0 power is equal to 1 for all x, including x equals b, right? So the thing is, this Taylor polynomial is supposed to agree with the function at x equals b. So if I plug in x equals b, I should get the Taylor polynomials, and hence the Taylor series, plugging into b should give you the same thing that the function gives you, f of b, right? And so the thing is, x minus b is equal to 0. And if you raise it to the 1 power, that's 0. If you raise it to the 2 power, that's 0. If you raise it to the 3 power, that's 0. So all of the higher powers of 0 to n will be 0. But the 0 power, 0 to the 0 here, we're assuming is going to be 1. So 0 to the 0 will be 1. And so when you plug an n in, you're going to have f of b divided by 1 times 1, and you just get f of b, right? So we need these things to be true in order for this notation to work. Let's do some examples and calculate some Taylor series. I need to calculate a lot of derivatives, right? Because every single one of these terms is a derivative, some derivative of the function evaluated at the point I'm interested in, and then dividing by n factorial, whatever. Here we go. So let's do e to the x, and I'm going to center it at x equals 0. So e to the x is, of course, the function. If I evaluated 0, e to the 0 is 1. The derivative of e to the x is e to the x. Evaluated at 0, that's 1. The second derivative is e to the x. So all of the derivatives here at 0 are 1. So all of these numerators are all 1. And I'm going to be dividing by the appropriate factorials, right? So it looks like 1 plus the derivative times x minus 0 plus the derivative over, so second derivative over 2 times x minus 0 squared plus the third derivative over 3 factorial times x minus 0 cubed, and so on. This simplifies to just 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Notice that you could write a 2 factorial here. 2 factorial is just 2 times 1, but it's 2. And likewise, you could divide by 1 factorial and divide by 0 factorial to make it all look like that. All right. So a couple things to notice. There is another term for Taylor series when you're centering them at 0. You'll sometimes see them called Maclaurin series. And also, I use an equal sign here. So I said e to the x equals this. And I really mean equal. You could think of it as the Taylor series converges to e to the x. In fact, it does it for all x. This is kind of an amazing thing about this particular Taylor series. Here's a graph of some things here. So, I don't know how well you can see colors here, but there's a black curve in here, which is e to the x. Okay, and so the red curve is the constant approximation, 1. The second curve here, this orange one, is just 1 plus x, so it's the linear approximation. And then 1 plus x squared over 2 is this yellow one. It's really hard to see, but there's a yellow parabola in there. And then there's a green cubic, and that cubic is just take the first 3. So I'm just looking at the successive Taylor polynomials and noticing that each one seems to be getting closer and closer to that exponential curve, both on the right-hand side and on the left-hand side, right? The orange, well, the red one just cuts through. The orange tangent line is probably good for a while, but then the blue parabola, no, the yellow parabola is next. It's good for a while. The blue's good a little bit longer. The green a little bit longer. Well, no, I guess green and blue. Anyway, they seem to be getting better and better, closer and closer. And it turns out that if you keep going, you keep taking x to the 4th, the 5th, 6th, 7th, and so on, that for every value of x, even ones, clear off to the right or clear off to the left, really big numbers, and eventually, if you take enough powers of x, that this Taylor series will converge to e to the x. And so plugging in a value of x on the left-hand side is the same as plugging it on the right-hand side. You get the same result for every single value of x. Kind of astounding. You might wonder why we would want to do this. One of the simplest reasons is, how do computers work? Essentially, computers work with ones and zeros, and the only thing they can really do is add and multiply. And so how do you do e to the x? Well, this is all adding and multiplying, right? Dividing is just multiplying by a reciprocal. Subtracting is just adding a negative. So anything that's multiplication, subtraction, addition, subtraction, multiplication, division, those 4 things are all essentially just addition or multiplication. And so I can evaluate e to the x by just doing a whole bunch of multiplications and additions. And depending on how accurate I need it, well, it might determine how many terms I need in the sum. Right? But at least it gives me a way of doing that. Turns out for each value of x, the infinite sum adds up to e to the x. All right. Now let's do another example with sine. So I'm going to start with my function sine. If I evaluate it at 0, again, I'm centering it at 0 here. Sine of 0 is 0. Derivative is the cosine of x. Evaluated at 0 is 1. Second derivative is minus the sine of x. Evaluated at 0 is minus 0. Well, minus 0 is still 0. And the third derivative is minus cosine x. Evaluated at 0, you got minus 1. And then the next derivative is back to sine x, which is what we started with. Evaluated at 0. And so your derivatives are just going to repeat this process. Every 4, you're going to get back to where you started from. Sine, cosine, minus sine, cosine, sine, cosine, minus sine, cosine. And you're going to get over here, when you plug the zeros in, 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. So when I create the Taylor series for the sine, it starts off with the constant is 0. The first derivative is 1 times x minus x0. Plus the second derivative is 0 divided by 2, x minus 0 squared, plus the third derivative is negative 1. That turns that into a negative 1 over 3 factorial x minus 0 cubed, and so on. And simplifying, I get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And I have this written out this way. The sum n equals 0 to infinity. I'm getting this plus or minus 1 by raising minus 1 to the n power. Notice if n is an even number, then minus 1 to the even power is equal to positive 1. And if n is an odd number, minus 1 raised to the odd power, there's going to be minus 1. So starting with n equals 0, it's going to start with a plus sign. And then with n equals 1, it's going to give me a minus sign. And then a plus and then a minus. To get these odd powers of x and these odd factorials on the bottom, I'm using the formula 2n plus 1. So in particular, when n equals 0, 2 times 0 plus 1 is 1. And so that's what I'm starting with, raising to the 1 power and dividing by 1 factorial. When n is 1, then this is 3, and then divided by 3 factorial. That's this term right here. When n is 2, 2 times 2 plus 1 is 5, so there's a 5 here and a 5 there. So that's just generating, 2n plus 1 is generating all the odd numbers as n goes from 0 to infinity. Couple things to notice here. Sine is an odd function. If you look at the graph of the sine curve, which I'll bring up right here. If you look at the graph of the sine curve, it's this black one. It's symmetric about the origin. That is, if I plug in a positive x and a negative x, the results, positive x and negative x, the results are opposite. Every time, no matter what x and minus x, you plug them in, you get opposite results. So the sine of negative x is minus the sine of x. This is what's called an odd function. And I find it curious, interesting, that the Taylor polynomial, Maclaurin polynomial, the Maclaurin series, centered at 0 here, has all odd powers of x. It's an odd function. Again, I use an equal sign because, like e to the x, this will converge for every single value of x, which is kind of crazy to me. I think of, graphs of polynomials with big powers can do lots of ups and downs, but sine does infinitely many ups and downs. And the thing is, you just keep getting more and more. The yellow is hard to see here. The red is the constant approximation here at 0. The orange is the linear approximation, so just taking the first, actually, constant approximation is 0. So the linear approximation is just the x. The quadratic approximation looks just like the linear approximation because the coefficient of the x squared is 0. So the next one you see here is the cubic. That's in yellow. All right, that fits in there pretty well. Fourth degree polynomial, of course, is no different than the cubic in this case. Then you have the fifth degree polynomial. That would be the green. Right? That green polynomial is amazingly good all the way from minus pi over 2 to plus pi over 2. And that, to me, says I can get pretty good approximations of almost any number because the sign repeats itself. And it also not only repeats itself, but it predictably goes downhill exactly the same way it went uphill. So if I needed to know the value of, say, what's the sine of 3, using that green fifth degree polynomial, it might say, well, that looks like it's pretty far off, but I could say, no, wait. The value of 3 being plugged in is the same as pi minus 3 being plugged in. And if I plug in pi minus 3, then that's going to be really, really good as an approximation, because you're going to be right in there close to that tangent line. So yeah, so even in a fifth degree polynomial, the sign can be very, very accurate for any x you want, as long as you know how to work your way down to this one region between minus pi over 2 and plus pi over 2. And I do want to say, yeah, I guess I did say this. I used an equal sign. Okay. So anyway, there's the green is the fifth degree polynomial and blue is the seventh degree polynomial. And that really hugs in there nice and tight for that, almost that full period from minus pi to plus pi. I think by the time I got up to a ninth degree one, it would be really, really good. So anyway, there's the sine. One thing I do want to point out about sine, which is kind of cool, compared to e to the x, that e to the x had powers of x divided by that same power factorial, but they were all plus signs and they used all the positives and negatives, right? There's an x squared, an x cubed. So the sine and the exponential are similar. It's just that this has only the evens. All right, next example I want to look at is the cosine. And the same thing, we'll just start with the cosine. You're going to take the first derivative, the second derivative, the third derivative, the fourth derivative, and so on. Evaluate them all at 0. This time it starts with a 1, because the cosine of 0 is 1. And then minus the sine of 0 is 0, minus the cosine of 0 is minus 1, 0, 1. Okay, so this is very similar to sine, which maybe shouldn't be surprising because the shape of the sine curve and the cosine curve are very much the same. Just shift it over. And so I've got a typo here that I'm going to change right now. And so we have the cosine is 1 minus x squared over 2 factorial plus x to the 4 factorial minus x to the 6 over 6 factorial, and so on. Very similar formula here. The minus signs, and again, the first one starts off as positive and then negative, so I'm just doing minus 1 to the n. But now I have all the even powers, so I'm just doing x to the 2n here, divided by 2n factorial. Couple of things. The graph of the cosine is symmetric about the y-axis. It is what's called an even function. You plug in a positive x and a negative x, you get the same results. Positive and negative, same results. So f of minus x is equal to f of x. Symmetric about the y-axis, that's what we call an even function. And look, the Maclaurin series has all even powers. Is this a coincidence? It is not. Right? Turns out that all even functions, when you find their Maclaurin series, will use just evens, and likewise odd functions will just use odd powers. But anyway, you can see a bunch of curves here. The red curve is the constant approximation at 0. The yellow curve, no, what's that? The orange parabola there is the second degree. The fourth degree is the yellow one that's barely visible in there. Then the green is the sixth degree, and the blue is the eighth degree. And again, by the time we get to that eighth degree polynomial, you've got really good coverage of that cosine curve from essentially minus pi to plus pi. Might need to go one more term to really get that whole one cycle of the cosine curve. Okay. Also, I noticed that the cosine is very much like the exponential in that it's just powers of x divided by that power factorial, except that this only uses the odds, and there's a plus or minus where e to the x has all pluses, right? So sine and cosine and e to the x. I mean, you'd expect sine and cosine to be related to each other and look kind of the same. You might not have expected e to the x to be so similar to them, but it turns out it is. They are all very, very closely related. Right? And like the sine in e to the x, that this converges for every value of x, the whole minus infinity to plus infinity. No matter what x you plug in, eventually you can find a polynomial big enough that this will converge very nicely. And in the infinite, it's equal if the polynomial is equal to that function cosine x for every value. Now let's do a little bit different one where it doesn't always add up right. This is Taylor series for 1 over 1 minus x. And we're going to center it at 0. So again, I'm doing a Maclaurin series. Here's f of x. If I take the derivative, think of this as 1 minus x raised to the minus 1 power. So I'm just using the power rule. So it's minus 1, 1 minus x to the minus 2 power times the derivative inside, but the derivative inside is minus 1. So that minus and the minus become plus. Right? They canceled out. And you just got that the derivative was 1 over 1 minus x squared. Likewise, you take the derivative again. There's a minus 2 that pops out. But then when you use the chain rule, there's another minus sign, which makes it a positive again. And so what happens is, each time we take a derivative, we just keep multiplying by the next bigger integer, because next time we're going to multiply by a negative 3. So we already had a 2 there, now we're going to multiply by negative 3. But then the chain rule is going to multiply by another negative, so then it becomes positive again. So the numerators just look like n factorial. So this is the third derivative, and that's 3 factorial. But then the power in the denominator is 1 more than that. So n and n plus 1. But what happens here, I'm going to evaluate each of those derivatives at 0. So I'm plugging a 0 in for x in each of these cases. 1 over 1 is 1. 1 over 1 is 1. 2 over 1 is 2. 3 factorial over 1 is 3 factorial. 4 factorial over 1. Whoops, I forgot to plug the 0 in there. But anyway, 1 minus 0 is still 0, is still 1. You raise it to the 5 power, is still 1, and we get 4 factorial. So the values of the nth derivative looks like it's n factorial. So when I make the Taylor series, it's interesting because each time you're going to take that derivative and divide by the appropriate factorial. So the second derivative divided by 2 factorial, the third derivative divided by the 3 factorial, the fourth derivative divided by 4 factorial, and so on. And so those all cancel out and just become 1. And you get that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth, and so on, which I can write in summation notation this way. This is the sum n equals 0 to infinity of x to the n. It turns out, though, that this only works for x between minus 1 and plus 1. It doesn't work if you plug in values of x outside of that range. Well, take a look at the picture here. Right? The graph of 1 over 1 minus x, there's a couple of things you might note. One, it's got a vertical asymptote at 1, because if you try to plug a 1 in there, you get 1 over 0, which is that vertical asymptote at 1. Also, as x gets really big, either positive or negative, the denominator gets really large, so 1 divided by a large number is going to be small. It's got a horizontal asymptote of 0. So the black curve here is this curve that we want. It comes from the inside there to that, and then this part over here. Right? So one thing I notice is that there's an asymptote at 1, and I'm centering things at x equals 0. So a polynomial that's passing through this point, I don't know how I'm going to get a polynomial to interpolate, to accurately represent a vertical asymptote. Polynomials don't have asymptotes. They don't head off to infinity at a finite point. They do on the ends, but not in the middle, right? So things are going to have to break down at this asymptote. What's curious is that just because we're centered at 0 and things break down at positive 1, it also turns out that things will break down at minus 1 as well. That as we get better and better approximations, again, I'm using the same color scheme where red is the constant approximation, and orange is the linear, and yellow is the quadratic, and green is the cubic, and blue is the fourth power. Right? They're definitely getting better and better approximations here, but they're not really converging that fast. I mean, think about how quickly sine and cosine sort of hugged in. The Taylor series, just they're hugged into that curve for quite a bit of time. It doesn't do that here. And it will eventually work its way down here, but this always is veering up or veering down. And it turns out it will never get past negative 1 to be any accurate. Once you get out here, just weird things happen. And likewise, certainly you're not going to be able to get into this negative stuff by plugging in something else. Well, I mean, think about it. Think about if you plugged a 2 in for x here. 1 plus 2 plus 4 plus 8 plus 16. I mean, that's not going to converge. That's getting bigger and bigger each time. You're adding on a bigger and bigger number. There's no way that's going to come out to be a finite number. So yeah, it doesn't work for x's out here. But inside, it does work just fine. Yeah, it works out really well. So what we're going to need to do in the next video is to figure out, when you've got a Taylor series, can we somehow decide what values of x does this work for? For what values of x does the series converge to the function, and for what values of x does it not converge? Okay. And that's what we need to do next.